This is 10.4, 10.3 parametric equations part 2. Let's recall we have a way to find the derivative of functions via the parametric form, right? So that is the x and y written in terms of functions of t. And I think we add this example here. So what we do is we've done A, yeah, we check the concave, whether the graph concave up, concave down at the origins. And so the answer is false. It depends on which part of the graph that we're looking at. Okay, so let's look at part B. Find the equation of the tangent lines at the origins. So once again, we're looking at the origins. There are two graphs that go through the origins. So if you're looking at this, you can see the graph has two parts. So you expect to have two tangent lines. So see, the graph's on the way up. I think that is the tangent. See there? See the graph kind of touch this graph right here on the way up. Okay, so that's the tangent line there. We also have the second tangent line if we are looking at the other part. You see this one kind of concave down, and I think the tangent look more like that one. Make it look better. Okay, so like this. Okay, there. Right, so it's got the touch origins at the second part of the graph. All right, so you can expect to see two tangents. One is more steeper than the other, right? Steeper than the other. And again, because at the origins, we have two t values that's associated with the origins, which in part A we saw. So namely, at t equals 0, right, at t equals 0, so on the way up, then we need to find the slope of the tangent line here, right? So what's the slope of the tangent line again? It's the derivative, and the first derivative this time. And what's the first derivative? We did the derivative with the first derivative. First derivative up here. See that one? 1 minus 3t squared over 1 minus 2t. Okay, so the slope of the tangent line we have found. Actually, you can redo it. It's pretty easy though. When you find the dy dx, right? All you do is take a derivative of y, and 1 minus 3t squared over 1 minus 2t is the derivative of that. Okay, now when t equals 0, you plug 0 in. It's 1 minus 0 over 1 minus 0. See, the slope is 1. So the slope of the tangent line there is 1. And since it goes through the origins, you see the 1 is set to 0. And therefore, the equation of the tangent line is just y equals 1x. Right, 1x plus the intercept is 0. And that's it. And you see that this is the slope of the tangent line. It's actually a 45-degree line. Now, in the second case, when the t equals 0, t equals 1, when t equals 1, we use the same formula, but with t equals 1 in this case. So t is 1. So m equals 1 minus 3t squared, so that's 8 times 1. 1 minus 2 times t, or 2 times 1. We got a 3 should be negative 2 over, that's negative 1. So see, that is 2. Therefore, slope is 2, so the function is y equal 2x. Plus, again, 1 step is 0 in this case. And that is the equation of potentializer. All right. Now let's move to the next topic. We talk about the arc length. So if you recall, an arc length, here's the formula from arc length. We call the Cartesian form. This one down here. Okay, that one's down here. Remember, the arc length is the derivative, sorry, the antiderivative or integral. The square root of 1 plus the derivative 1 back to x squared. Now, so what happened is, going from this formula, then we use the information that we learned in this section. What is dy dx again, right? So dy dx, it's dy dt over dx dt. Okay, the parametric form what we have over here. So if dy dx is this, and I can do, okay, so see that if we plug it here, then what happened is we got square root of 1 plus that square. Okay, and what I can do is we're gonna combine, maybe let me do this, then you square that. Right, so what you have is dy dt squared over dx dt squared. Okay, now notice that we add 1, right? We add 1. So what's inside is, let's say we add 1, and to convert to common fractions, common denominators, and think of 1 as dx dt squared over dx dt squared. Right, so there's 1. So then you have this underneath the square root. They have the same denominator. So that becomes dy dt squared plus dx dt squared all over dx dt squared. Now notice that there's everything inside the root, so technically square root there, square root there. The denominator, when you take the square root, right, of dx dt squared, it becomes just dx dt. So I have dy dt quantity squared, and then dx dt quantity squared over square root and square cancel. You have dx dt there. And don't forget that the integral should look like this, dt. And when you divide by a fraction, you multiply by the reciprocal. So this is the x there, so right, this is the x. Right, from here, and then you times dt dx. So dx got cancelled, you left with dt, this quantity, and that is this formula here. Okay, so basically, I'm plugging the derivative in parametric form. We derive this formula, and from now on, when we need to find the length of arc length of curve, I can use this, the alternative form or variations of the arc length using this formula. So formally, if a smooth curve does not intersect itself on the interval from A to B, except possibly at the endpoints, then the arc length is given by this formula, right? Okay, so it should be easy though to memorize. It's just the derivative of x squared plus derivative of y squared. Now let's look at an example here. So I'm going to use the same example as this one above. Okay, the same as the example here. So let's say I have the same functions, x equal t minus t squared and y equal t minus t cubed. And I want to find the length of the loop. Okay, so what I do is I want to find this loop right here. So that one. So as we know, when t equals 0, okay, we are at the origins, right? So it go back, and then when t equals 1, it's back to here. So when t equals 0, we're at the origin. When t equals 1, back to the origin. So the complete loop. So if we're going to find the arc length, then by this integral, by this formula, it's integral from 0 to 1. Okay, from 0 to 1, square root of derivative of x squared. Derivative of x is, with derivative of x is this one, right? So it's 1 minus 2t squared plus derivative of y squared is 1 minus 3t squared dt. Now, technically, the setup is very simple, all right, like that. But to integrate this, it's going to be a different story. Then this example, I don't think we can do it by hand. So you can use calculator to approximate this integral. Okay, use calculator. We don't have a formula or any individual technique we learned in previous chapter to tackle this integral. Okay. Now next, and the final topic is the surface area. Okay, it's the surface area. Now recall in surface area, it's 2 pi radius. Let me see, we forgot. The surface area in general is 2 pi radius times the arc length. 2 pi radius times the arc length. Okay, so we have 2 pi radius times the length. The length in this case now is this integral, right? So now all you do is involve 2 pi, just add 2 pi, the radius. Now I have two formula here, the y, the x. It's because when you rotate around the x-axis here, then you see the radius is here, the y coordinate of this point, so that will be the y here. If we rotate about the y-axis, okay, when we rotate about the y-axis, right, so the radius is this distance, so that is x. Okay, so we have either 2 pi y or 2 pi x, depends on which axis rotations we resolve. Okay. All right, so let's look at the quick example here. Let's say, to make things easy, I'm gonna use exactly the same example up here. So let me label it in its so label it C. So like A is the concavity, B is the tangent line, C we have the length, arc length, and now we have D, we find the area of the surface. Generated by rotating the curve on the interval from 1 to 2 about the y-axis. Okay. Right, so what do we know? Again, what we know is at 1, we at the origins. Okay, so at 2, we think it's going to be somewhere over here. So from 1 to 2, you actually have this curve, or this lane. Okay, and you rotate about the y-axis, and I think we got a bit more so like a cone. Okay, cone, right? So we're gonna find the area of the surface, right? Because rotate by the y-axis, so the radius will be x. So the formula will be, see, the same as arc length. All you do just include an extra 2 pi x. So the surface formula is integral from, okay, t is 1 to 2 pi x square root of, again, the same as that one up here. It's 1 minus 2t squared plus 1 minus 3t squared dt. Now, one thing we have to change is because of the variable of integrations is t, so you cannot have an x there. So I'm going to simplify a little bit. Let me take out the 2 pi. So that's 2 pi integral from 1 to 2. And the x, what is x? X is t minus t squared. So we write x as t minus t squared. And then the time. This again, 1 minus 2t squared plus 1 minus 3t squared dt. Once again, this calculator, this is the problem is complicated, so we're going to do this on the calculator to approximate the answer, right? And finally, I think I have an example here. Basically, you gotta just be summaries of all that we have learned in this sections, starting with the same parametric curve, and then we're gonna do, I'm gonna do 1 and 2 quickly, but the rest is just more like a review. Okay, so again, find the arc length, the length of the curve on the interval from 0 to pi third. So first and foremost, when you do this problem involving the calculus, you need to find the dx dx and then dy. Okay, so I'm going to do this here really quick on the side first before I do anything. So what is dx dt? Okay, so derivative that one, right? So derivative this 3 times cosine. So you get 3 times cosine of 2t, new side cosine, and by chain rule times 2. So I could have 6 cosine 2t. And for the dy dt, we have negative 4 times sine of 2t. Again, by chain rule times 2. So that would be negative 8 sine of 2t. Okay, so you got that part done. Okay, think at first. Now, all the answer that we do will be using these informations. Find the arc length. Okay, so at the formula again, the arc length is the integral from, it's given from 0 to pi third, so 0 to pi third, square root of dx dt squared, right? So it's gonna be 6 cosine of 2t squared plus negative 8 sine of 2t squared dt. Right, so that's the setup. Again, we probably use calculator to finish that problem there. Right, number 2, find the area of the surface formed by rotating the arc on the interval from 0 to pi third about the x-axis. Okay, so when we rotate about the x-axis, then we will have a 2 pi y, 2 pi y, I'll leave the space there. Okay, 2 pi y times square root, again, it'll be this. Okay, that square plus that square. Let me simplify this time. It's already 36 cosine square of 2t plus that is 64 sine square 2t dt. But once again, you don't want to leave the y's there because the variable is t, so the y replaced by negative 1 plus 4 cosine 2t, like this. I'm going to take a 2 pi outside, negative 1 plus 4 cosine of 2t. Right, so that is the setup. Okay, again, the rest is actually the same as we did earlier. Number 3, find the tangent line. To find the tangent, coefficient tangent, you need the slope. To find the slope, you need the derivative, and the derivative is dy dt over dx dt. So that is negative 8 sine of 3t over 6 cosine of 2t. Okay, and then you figure out t value, plug into the slope, and then we got the equations. All right, so that would be the second part of 10.3.